M-Cube seminar, and this is joint with JCSDA. So I'm pleased to welcome Neill Bowler. Neill studied for a Bachelor's of Science in Physics at University of Warwick. And I got this bio from him, so I'll quote, "However, that didn't put him off, so he also completed a PhD at the same university." So, immediately after that, he joined the Met Office and started working on the nowcasting of precipitation. He then spent many years working on the NWP ensemble prediction system of the Met Office, initially developing the ETKF system and then replacing this with an ensemble of data assimilations. More recently, Neill's been working on the use of radio occultation observations and helping with the migration of the Met Office to using JEDI. Welcome.
All right, so thanks very much for the welcome, and yeah, thank you for having me here, and I appreciate you all showing up online and in person. So I'll be talking about really very much the plans for our development of the ensemble system within JEDI at the Met Office. I don't have a huge amount of results, so I'm going to let you know early on this is more about the plans and less about how far we've got so far. I also want to say I really appreciate it here in sunny Boulder. The weather has been lovely. There's only a little bit of rain today, but generally very sunny. Whereas this is the weather forecast and for where I've come from, and the point here is Exeter, and you can see, it's basically under the rain today, under the rain tomorrow. We get a little respite on Saturday, and then it's raining again on Sunday. That is the weather I've left behind. So what am I going to be talking about? I'll give a very brief description of what we have now. I'll talk about our plans to remove the deterministic forecast from our system. I'll then describe the mean-pert and control-pert algorithms, which are kind of the useful tool we have for generating our global ensemble, and the tests that we've been doing within JEDI to validate whether control-pert is doing what we would expect it to and behaving in a sensible way. Then I'll talk about a few problems we have with the current system to do with additive inflation. And then finally, a kind of little bit about our plans for the UK ensemble and how we're going to be developing that. So the current system, we currently have a deterministic system that runs a hybrid 4D-var data assimilation, and that runs at 10 kilometers. And the ensemble is then run at 20 kilometers, and it's using a hybrid ensemble of 4D ensemble vars. Don't worry, I will explain those horrible words in a minute. We're using the mean-pert method, and we are not using any perturbations to the observations. We're using various things to replicate a deterministic ensemble Kalman filter and inflation schemes. We have a scheme called additive inflation that I will explain later that is quite important. It's a scheme for supplementing the stochastic physics to try and simulate the error in the model. And interestingly, that's the system that we have at the moment. We have an ensemble of data assimilations, and they're all producing their own analyses. And that therefore gives us an analysis from the ensemble, and we use that ensemble mean analysis. But because the deterministic system is run at higher resolution, that's also a really good analysis. So when we're recentering the ensemble, we actually recenter it on the average of those two analyses. Now, the ensemble of 4D ensemble vars, we developed it because the 4D ensemble var method is cheaper than a full 4D var method. You don't have to run a tangent linear adjoint. But I will say it is not particularly cheap because it does require a lot of I/O. And as I'm sure many of you will know, supercomputers don't like a lot of I/O. So that's kind of one problem with the system as we have it at the moment. So I'd like to just take a minute to describe some of the words I used around the data assimilation schemes. So data assimilation, you have a sequence of observations within a data assimilation window, and you're trying to find a state that best fits those, given your background forecast. So with a 3D VAR system, what you're doing there is you're saying, let's take the state at the middle of the data assimilation window to be representative of the state within that whole time window. And we will assume all the observations, although they're taken at different times, effectively we're assuming they're taken at the middle of the data assimilation window. We then have a variant called 3D FGAT. So FGAT stands for first guess at appropriate time. And that's where you're still assuming you're trying to get a state at the middle of the data assimilation window, but the background forecast that you're using, you're allowing that forecast to vary across the data assimilation window. So you're using the time variation in your background forecast to allow you to kind of understand the variation in the observations a little bit better. Now, actually, the scheme that we use for the deterministic system at the moment is called 4D VAR. So with 4D VAR, you're assuming you have a state at the start of the window, and then you're using a linear model to propagate that state through the data assimilation window. And that linear model is also allowed to propagate the covariance information throughout the data assimilation window. We do use a hybrid 4D VAR system, so we are using information from the ensemble to inform what the error covariance is at the start of the data assimilation window. But we are very much relying on the tangent linear model to propagate that information through time. Where 4D ensemble VAR is cheaper is you have the trajectory of ensemble states throughout the data assimilation window, and you're using that trajectory of states through the data assimilation window to understand how your errors propagate through that window. So you're not relying on a tangent linear model, which is expensive. You're relying on the ensemble forecast that you already have to do that time propagation. Now, Andrew and Mohammed did spend some time fairly recently looking at a comparison in a deterministic data assimilation system of which of these various methods of doing data assimilation is the best. So what this plot is a little bit complicated. What it's showing is on the y-axis you have the quality of the forecast. So the further up the y-axis, the better the quality of the forecast, and this is measured over a kind of basket of scores and basket of lead times. And on the x-axis, you have the amount of weight you're giving to the ensemble when you're calculating your covariance information. So if you start on the full left, so hopefully if I can get my pointer up, here you go. Here on the left here is a pure 4D VAR data assimilation scheme. So that is using a parameterized covariance model. It is not using the ensemble information at any point. And it is using the tangent linear model to propagate that covariance information through the DA window. If you then kind of look down, this green dot here, that is a pure 3D VAR system. So you're not having any time propagation of information, and you're just using your parameterized covariance. Now, if we hop further onto the right-hand side, this red dot here, this is 4D VAR, but you're fully using the ensemble covariance to inform what the errors are in your background forecast. And then a 3D VAR, but where you're using the ensemble covariance fully, is this green dot. Now you see the green and the blue are much closer to each other on this right-hand side than they are on this left-hand side, because the ensemble information is giving you a lot of kind of useful information that the 4D VAR is actually inferring from its tangent linear. Now, our ensemble update uses this purple dot, which is 4D ensemble VAR, but we are using a hybrid version. So if you go somewhere to the middle, you're in the hybrid schemes where you're using partially ensemble covariance information and you're using partially the static parameterized covariance information. And what we've seen here is that whilst if you're fully at the ensemble side of things, there is not a huge amount of difference between the different algorithms that you could use. If you're in the hybrid regime, then 4D VAR seems to be the clear winner, and 4D ensemble VAR is noticeably quite a bit worse. And the reason for that is that if you're using that static covariance information and you're not propagating it through the window with the tangent linear model, then you lose out in a lot of forecast quality. So this, as much as anything, was the motivation as to why we wanted to stay with hybrid 4D VAR for our central or best estimate system, but also why we think, well, 4D ensemble VAR and 3D VAR, they're not hugely different, at least not when you're using covariance information. So onwards to carry on describing, so that was all really kind of for the global model. What do we do with our UK model? So our UK model is a 1.5 kilometre resolution system, and it is a 4D VAR. So it is a 4D VAR without the hybrid part of it. It is just a straight 4D VAR system. That is cycled every hour, so that 4D VAR data assimilation is running every hour, and then we run long forecasts every 3 and very long forecasts every 12 hours. There is a large-scale blending system that we use to help get background information from the global model into the UK analysis. And then we have the UK ensemble. That's run at slightly lower resolution, but still some kind of convection permitting. And interestingly, that's run 3 ensemble members every hour. So it's kind of an incremental drip of ensemble information coming in. And that uses the UK analysis, but with added perturbations from the global model. So effectively, it is very much like a dynamical downscaler of the global ensemble prediction system. So now for a really messy graph. This shows the time variation of when everything is run within the UK system. So up the top, you have in the black bars when we are running our global deterministic model. The global ensemble is then the red bars that run after that. And then the little blue bars, that is when the UK analysis is run. So that's run every hour throughout the day. And the numbers underneath the blue bars, they are the 3 ensemble members that are run in that hour. So if we look, say, here, here we go. For the 6 UTC run, you're running ensemble members 3, 4, and 5. But that's running using so it's using perturbations 3, 4, and 5 from the global model, but added to the 6 UTC analysis from the UK data assimilation system. Now, the interesting thing is actually this bit up here is about to change. So in the near future, we're going to be moving to a 3-hourly cycling system for the global, because one of the things that determines the quality of the UK forecast is those lateral boundary information that's coming in from the global system. So if you're running it more regularly, so you're getting a fresher update of information, then the UK forecasts get better because they're receiving that fresher lateral boundaries. Now, one of the things that we hope to do in the near future is to retire the deterministic. So the motivation for doing that is very much as anything, a scientific one. We all know that the forecasts are uncertain, and without an estimate of uncertainty, then it's not really a complete forecast. But also, we have a number of customers within the Met Office, and those customers over time are gradually becoming more intelligent about the forecast they're receiving and capable of receiving probabilistic information. So there are more and more people who are actually asking for this kind of information. We also hope to have the idea that we are embedding ensemble forecasting within the heart of our production process. So if we say we no longer have a deterministic forecast, then we are really orienting ourselves from an organizational point of view towards producing uncertainty information and embedding that within the way that we do our business. Now, there is also, I put on this last one, and I'm sure it will be controversial. We don't want to run within the convection grey zone particularly. So at 10 kilometers resolution, you are partially resolving convection, but not really. And so you have a convection parametrization. When you're at 1.5 kilometers, you're more or less resolving convection, so you don't need a convective parametrization. When you're at 5 kilometers, you're halfway between the two, and do you need a convective parametrization? And so from a modeling point of view, that's a very tricky place to be. So there is a kind of desire to keep it out of the way of that. So the plan of how to achieve that is that when we have our next supercomputer, we will upgrade the ensemble to be running at a higher resolution, so 10 kilometers in the global and 1.5 kilometers in the UK. And then the control member of the ensemble will be kind of effectively the same as the deterministic system is now. So if somebody really wants a single scenario, you can offer them the control member from the ensemble, or you could offer them the ensemble mean or something like that. But that's a kind of the second step. By default, we want to be offering people an ensemble product rather than just a single scenario. So what's next? What do we hope to achieve in the global ensemble? So we are thinking that the control member will stay effectively similar to the deterministic as it is at the moment, so with a hybrid 4D-var data assimilation scheme, and it will be running at about 10 kilometers. Now you may notice I've changed the name. It was N1280, it now becomes C1000. That's because we're moving from the unified model system that's run on a latitude-longitude grid to the ELFRIC system, which is run on a cube sphere grid. So 10 kilometers is what's notationally known as around C1000 resolution on that cubed sphere grid. Our first plan is then that we will have a 3D-var based ensemble that is running using what's called the control-pert method. So we'll be running at 10 kilometers, but we will be using the control-pert method to update the perturbations with a 3D-var data assimilation scheme. We intend to be using perturbed observations and an RTPS scheme for inflation. And then we will simulate the model errors using a combination of additive inflation and stochastic physics. Now, there is an uncertainty here because we don't fully know whether the control-pert system will be behaving as we necessarily would want it to. So the backup solution is to run a hybrid 4D-var ensemble. So all ensemble members will be independent of each other and running as kind of good a data assimilation system as we can do. So the question is, which method are we going to go with? So you could have an ensemble of independent 4D-vars where each member is running its own data assimilation. That is very similar to the system that ECMWF use at the moment. Or we could have something that's a bit more similar to what we're using at the moment, where you say you have a good 4D-var analysis for the control member, and then you have a cheaper analysis like a 3D-var system for updating the perturbations to that control member. Now, computational cost, computers are not infinite. So no matter how big a computer we have to make compromises somewhere. So either we make a compromise, say, in the ensemble size or in the resolution of the data assimilation update, or we make a compromise in the quality of the update method that we're making to the perturbations. And so that's what control-pert is about. It's allowing us to update those perturbations with a cheaper method so that we can afford to make sure we have a really large ensemble and therefore kind of put the extra computational power into that. So I've talked about mean pert and control-pert. Let me try and describe those in a bit more detail with some equations. So if we have our updating an ensemble member, then if we could take the Kalman gain type formulation, then the analysis increment for that ensemble member would look something like this. So this here is the analysis increment for ensemble member K, and that would be equal to these terms here, the background and observation error covariance matrix and the observation operator. So these terms here are effectively the Kalman gain. and then that's multiplied by the observations, y, plus any perturbations to the observations, and then minus your background forecast from the ensemble member. And I've split the forecast from the ensemble member K into the ensemble mean forecast plus the perturbation for ensemble member K. Now, you can see fairly readily, if you take the ensemble mean, the analysis increment for the ensemble mean would be that Kalman gain term as before, times by the observations. These perturbations to the observations you would expect to average to 0, so that term disappears. And similarly, the perturbations you would expect to average to 0. So your update to the ensemble mean is just the observations minus the model forecast of the observations. Now, if we subtract these two from each other, then you get an analysis increment for the perturbation for ensemble member K. And that's again the Kalman gain term, but we lose these mean terms now and we just have the perturbation terms here. Now this assumes H, the observation operator, is linear, but that's hopefully a fairly reasonable assumption. So that gives you a way of updating just the perturbations without doing a full analysis. Now this is the kind of the Kalman gain way of writing the equations. We could, of course, also write those in a variational format where we find the increment to the perturbation K by minimizing this cost function here. So this is the same form of the cost function as variational dA, except we've substituted a few terms. So rather than updating the background forecast, we're updating the background perturbation. The observations, instead of being assimilating observations, we're assimilating perturbations to the observations. And rather than using the full observation operator, we're just using the linearized form of the observation operator. So that's very, very similar to kind of what we normally use in variational dA, but with just a kind of few substitutions. So that was the mean PERT algorithm. What is control-pert? Essentially, it is the same thing. If you think about it, if we're going to a system where our deterministic forecast is really the control member of the ensemble, then it might be natural, rather than linearizing around the ensemble mean, we might want to linearize around the control. So the advantage of that is when you're running, say, quality control, it's often very useful to have a realistic model state that actually looks like an atmospheric state as the background for your quality control algorithms. Whereas the ensemble mean might not necessarily have a particularly realistic dynamical state in the same way because it's a statistical average. So the theory for control-pert is essentially the same as the theory for mean PERT, but rather than having here this subtraction of the background for member K from the mean, you're having the subtraction as the background from member 0. And so the perturbation is then just defined relative to member 0 rather than being relative to the ensemble mean. And then basically everything else flows in the same way. So that control-pert algorithm has been implemented in JEDI. Now one basically linearizes around the control member background, reads in the observations, calculates the background error covariance and observation error covariance matrix and the linearized observation operators. And then you set the observations to 0 and you set the background that you're doing the assimilation from as the difference between the ensemble member and the control. And then once you've done all of that, essentially you're able to then use the same mechanics within JEDI as you're using for doing a normal data assimilation. So that's the real advantage of doing this. We're able to very much reuse the same kind of mechanics as we normally use. Now, the control member can use any data assimilation method it likes, but the coding at the moment for the control-pert algorithm means that the pert update, so the update for the perturbations, has to be constrained to using 3D var. If we think control-pert is a very promising avenue, then we may put more effort in and allow it to, say, use a 3D FGAT or maybe a 4D ensemble var update. But for now, it is just a 3D var update. So aside from coding this, we've started running some tests within the NWP system. Yes, Chris?
In control-pert, do the perts have zero mean?
So the question was, if anyone didn't hear that, in control-pert, do the perts have zero mean? And thinking about it, I think the answer is no, they don't have to have zero mean. We may choose to reset them to have zero mean, but I think by definition at the start of the data assimilation, there's no requirement for that.
Thanks.
Okay, so what tests have we been running in our NWP system? So far to test out the code, we have just run a single cycle. So we've run both the control-pert and an ensemble of independent data assimilations using identical backgrounds and using the Elfric model at a relatively low resolution. And then we've tested that with a relatively small set of observations. And we're comparing the analysis increment that we get out from the ensemble of independent data assimilations with the equivalent member using the analysis increment to the control plus the analysis increment to the perturbation. Because if everything is linear and straightforward, then those should be the same numbers. And we're using 3D var in all cases with both the ensemble of independent DAs and with the control-pert. So because they are essentially the same, you would hope that you would get similar answers. So what's being shown here is a vertical profile of the root mean square of the analysis increment at each level for various different variables. Now, I'm sure you probably can't see which each variable is from the back. So this is potential temperature. This one here is Exner. This here is density. This is specific humidity. And then you've got northward and eastward winds. And they're going from the ground at level 0 all the way up to level 70, which in our model is around 80 kilometers. And there are two lines. The control-pert is in blue and the ensemble of independent DAs is in red. And most of the time you will see basically just the red line because the two are more or less lying on top of each other, which is very encouraging because we're getting essentially very similar increments between the two. This is for an experiment where we're just assimilating observations from the ATMS set of instruments. But of course, there are differences. So if we look at density here, there are slight differences between the two lines where you're getting a different RMS increment from the two different schemes. And similarly, for specific humidity, we seem to be getting a larger increment from the EIDA than we are from the control-pert algorithm. Now, initially, this did worry us because it was a kind of significant difference, but you do expect most non-linearity in specific humidity. However, because this is ATMS, the actual magnitude of the increments that you get out are relatively small. So although it kind of looks bad for ATMS, it is a relatively small fraction of the total increment you get for specific humidity. Then if we move on to look at a similar plot but for radiosondes, you can see it looks slightly different. So the specific humidity plots look very much closer than they were, but the Exner function plots look a bit more different. So we're getting slight differences in the increments, but again, they're not huge. And then there's a test where we run with all of the observations that we have at the moment. So this is the set of observations is shown up here at the top. A kind of a basket of representative but set of observations, but not all of the ones that you might want. And again, you can see that from an RMS point of view, we're getting very similar increments between control-pert and the ensemble of independent DAs. So that's very encouraging for us. However, if you kind of plot a map of the two increments, you'll see that there are some differences. So the left-hand side, you're getting the analysis increment from the ensemble of independent DAs, and on the right-hand side, that's the difference between that and control-pert. And so you can see that there are some definite differences between the two systems. They're not large. The difference between the two analysis increments is definitely smaller than the analysis increment itself, but they're still there. But overall, we would say that when we're using the same method, because here we're just using 3D VAR in all the schemes, we kind of have a fairly clean bill of health. We are getting small differences between the analysis increments from the two systems, but largely it's okay. Now, because we're using the same data assimilation system, effectively what we're really doing is just testing the nonlinearity of the observation operator. So what happens if we actually use a different data assimilation scheme for the control and for the EIDA? Well, again, if we look from the vertical profiles of the analysis increments, they look fairly similar as before. So we think, oh yes, this is very encouraging. But if we then plot a map, we again get definite differences in the analysis increments. So again, this is the analysis increment from the EIDA scheme, and then this is the difference with the control-pert. And these differences here, they are slightly larger than what we were seeing before. But also, the EIDA is producing us different increments to what it was before, because now it's using a 3D FGAT scheme, whereas before it was using a 3D VAR. So if I flick between the two, you will notice that, yes, the analysis increment on the left is changing, but also we do get slightly larger differences between that and the increment from the control-pert scheme when we're using 3D FGAT. So we look at those and we say, well, do we have a clean bill of health? We're not entirely sure yet, but so far it's kind of looking like control-pert is giving us something that's at least close to what we're getting from an ensemble of independent DAs. Is it close enough? I'll let you know in a year's time when we've made up our mind. So I wanted to just give a little kind of notes on a couple of things that caused us problems on the last time. So when we were updating our ensemble system to the one that we are currently using. So at the moment, our system does not use perturbed observations. So we ran various tests testing the impact of perturbed observations on our scheme. So we had a system where we had an ensemble of 4D ensemble VARs. We were fully recentering on the deterministic assimilation. We were using additive inflation, and we were using RTPS for inflation as well. And then we said, well, let's take that system and let's add on perturbations to the observations. And what happens to the ensemble spread? And the answer was basically nothing. We didn't get any increase in the ensemble spread from having those perturbations to the observations. And what's shown on the right is a scorecard. So it's the change in the continuous ranked probability score for various quantities of various lead times for adding those perturbed observations. And if you're used to looking at scorecards, you will look at that and go, there's nothing to see there. And that's the truth. There is very little to see there. So we have always scratched our heads and gone, yeah, we'd like to use perturbed observations, but we don't really understand why they didn't work last time round. The other thing that is kind of a key in our system is additive inflation. So this is a scheme where we're supplementing the stochastic physics to try and represent model error. So the way we do that is we take an archive of analysis increments that have been taken from the previous year, but from the same season as we're currently simulating for. And then we just basically randomly sample those analysis increments. And then with some kind of calculations around the mean analysis increment, we then scale them back and then add them to the forecast. So those scaled analysis increments are being used to nudge the forecast as a way to kind of help simulate, at least from a statistical sense, model error. But we have a bit of a problem. So the problem is, and this I think is a kind of philosophical problem for stochastic physics overall. So if we consider ensemble member number 1, then for that ensemble member, we are perturbing it. So imagine this is the dark green is the data assimilation cycle. And then for the next 6 hours, we're adding gradually an analysis increment for that 6 hours. And then for member 1, at the next 6 hours, we're choosing a different analysis increment and we're adding that on again. And then for the next 6 hours, and so on. And we have a different set of analysis increments that we're choosing for ensemble member number 2. Now we then come to do data assimilation 6 hours later, and the background that we're using for ensemble member number 1 has already been perturbed by this analysis increment. So when we're running then the subsequent forecast and we're doing all the DA, we need to keep on adding that analysis increment to the trajectory of the system, or else the background will have the perturbation in it from the analysis increment. But if you then get rid of that when you're trying to run your analysis step, your background is not going to be consistent with your analysis, and so then you'll have a problem. So as soon as you have your analysis increment in the forecast, because it's then affecting your background trajectory, you need your analysis increment in your assimilation window. But that then causes us a problem because the additive inflation scheme doesn't know anything about today's weather. It is just a randomly picked analysis increment, scaled and messed around with in some ways, but it's just a random analysis increment from an archive. So it may well add kind of large increments into the center of a high pressure system where it's really not appropriate. And what you tend to see is if you just take a random analysis increment and add those to an ensemble, the spread will actually decline as those inappropriate increments are just kind of shaken out of the system. So what we're doing is we're actually conditioning our ensemble DA system not to grow because we're adding things to it that don't grow over time. So what we'd really like to do is find a way to get the additive inflation scheme out of our DA cycle and keep it as only part of the ensemble forecasting system rather than the ensemble DA. Now, whether or not that applies to stochastic physics is a matter of debate, because whenever we run stochastic physics, okay, it does know about today's weather, but at the same time, the random seed that we use for the stochastic physics, that changes every cycle. So our background trajectory has a certain set of stochastic physics random numbers in it, and then we change that when we're doing the analysis. So it's a kind of a bit unclear as to what's the right thing to do there. Now, this additive inflation scheme is a bit unique to the Met Office. We have tried many, many times to get rid of it and replace it with proper stochastic physics or something else. But generally, they just didn't work. So we're kind of stuck with the scheme as it's the best thing we've got to model our model uncertainty, but it's kind of got its limitations at the same time. So that was all about the global ensemble. Let me talk a little bit about the UK ensemble and our plans therefore. But I'll actually start with the UK data assimilation, because one of the unique features we have with the UK data assimilation is the large-scale blending scheme. So you're running the global model every 6 hours, and that's providing lateral boundary conditions to the UK system. Now, up until when you're running, say, the 0, 2, 3, and 4 UTC cycles for the UK, they're all taking their lateral boundary conditions from the 18 UTC global run. And then you run the 0 UTC global run, and that will provide lateral boundary conditions for the 05 UTC UK run, and 06 and 07 and on forwards. So suddenly, the 05 UTC run is getting this brand new batch of lateral boundary conditions, which is providing it a bit of a shock. And of course, the global system has updated its larger scales. So what you want to do is you want to be able to say, UK system, here's a new data assimilation cycle coming in from the global. Let's update the UK so that it knows about what's going on. So the way we do this is what we call large-scale blending. So what you do is you start with the global analysis, and then you add to that any kind of fields that are specific to the regional model that are not present in the global. And then on the UK system, you run a short-range forecast. So you're running a short-range forecast in the UK system from the global analysis. You then take the forecast, the background forecast that you had from the 4 UTC cycle, and you take the difference between those two. And that difference is going to give you effectively what is the analysis increment on the globe from the global system, but running within a UK context. We then filter that to just include the large scales and reduce it slightly in scale. That can then be added to the 4 UTC forecast, and then you kind of rerun the new forecast with a new background. So when you're starting that 5 UTC analysis, it has already received that analysis increment from the global. And so the UK analysis doesn't have to update the large scales because the larger scales have already been updated for it from the global. And we ran various tests with that, and this is another scorecard, but it's a scorecard for the UK model. And generally, all of those triangles are pointing upwards, which says that actually this change to injecting the large-scale information from the global has been very much a positive change. So one of the problems that we have with the UK system is a lead time problem. So the UK system, if we're running data assimilation for it, and we're running our data assimilation every hour, the benefit of that data assimilation is actually quite limited in time. Because we're running on a regional model, it's analysing the small scales, and over time they become unpredictable, and new information wipes in from the lateral boundaries. So you only get 12 or maybe 24 hours worth of benefit out of the UK data assimilation. And our current scheme does struggle with tracking the convection properly because it's based on a kind of parameterized covariance system. It's not a hybrid data assimilation scheme. So our plan over the next coming years with the transformation to JEDI is to focus our data assimilation effort at getting a good short-range forecast for the UK. So one of the aspects of that we think is critical is to get good background error covariances. So we're trying to think about running an ensemble system that is really able to represent those convective scale features. Whereas our current ensemble system is very much run for the medium range, and it's really only a dynamical downscaler, so it's picking up those larger scale perturbations. So we really want to kind of transform the system to be looking at those smaller scales so that it can get a good short range forecast, and then you run the global downscaler that will give you a much better medium range forecast. So as a schematic of that, it's shown here. So the blue line is a kind of a traditional nowcasting system we call the meso analysis that will give you a good short-range forecast coming from the observations. The green line is the current dynamical downscaler NWP system that we have. And the idea is to create an extra ensemble prediction system that we're calling the NWP nowcasting ensemble that will gradually hand over between those two. So it will deal with the short-range forecasts and try and give us added value. So this is the timescale of how we're attempting to do it with our transition to JEDI. So in the near term, what we call Horizon A, we're hoping to develop an ensemble Kalman filter-based system within the JEDI system, and to just kind of get that up and running and performing in a reasonable sense using our UK model. And then once we've kind of got something as a baseline that we can build on, we start to ask the science questions of, can we really get that performing and providing good convective scale forecasts? So we'll be looking at things like trying to assimilate a lot of radar reflectivity information. That often comes with horizontal correlations in the observation errors. So correlated observation errors is a kind of key work package within that. We'll look at the large-scale blending that we're using. We'll look at how we're doing the localization to try and make sure that the assimilation is focused on getting those smaller scale features right rather than trying to correct the large scales that are coming from the global. And all of this, we're hoping to do that in conjunction with the forecasters in the operations center, so get their understanding of what they think is a good system and make sure that we're providing them with a good product that they can use. So that's it for me. We're transitioning to using JEDI from our current systems, and we're using this as an opportunity to redesign our ensemble prediction systems. We're very much committed to embedding ensemble prediction within the heart of what we do. So we're planning to kind of retire the quote-unquote deterministic forecast. And then we've got a lot of bullet points there that I talked through about how we're changing the global ensemble prediction system and how we're changing the UK one. But I'll leave it there. Thank you very much all for your attention.
So thanks. There's been some experiment at ECMWF with the EDA, and we know it is an ensemble of 4 divars with outer loops, and they tried running without the outer loops, and it was clearly very detrimental. And the fact that we have an ensemble that's nonlinear, the 4 divar with outer loop is a nonlinear data assimilation system. And the fact we have a nonlinear ensemble for these outer loops in the EDA is a big factor in the skills of their ensemble. So, and I see with your control-pert and some of the things you're doing, you're trying to make your ensemble much more linear. And especially when you're going to a regional where things are more non-linear, it's in very contradiction. They're trying to make your data assimilation very linear, whereas the problem you're trying to solve is becoming more nonlinear, and having an EDA with outer loop would capture that nonlinearity.
Well, in a sense, this is where, of course, we have to admit that the Met Office is behind ECMWF, because even in our deterministic data assimilation system, we don't currently have an outer loop. Some of the reasons behind that are technical, but there are kind of some scientific reasons behind it as well. In a sense, all of the effort about control-pert is we're assuming that if we're only updating the perturbations, then we can do not as good a job as necessarily we would do with the central estimate, because this is just it's the second moment of the distribution, so getting that exactly right is not as critical. But you might be right. It may well be that actually what we do need for understanding the uncertainty is to have a system that is nonlinear and understanding the nonlinearities as well. I think, I don't know, we will try the experiments. We will certainly continue the comparison between control-pert and EIDA. But yeah, certainly from my perspective, the cost of running an ensemble of 4 divars, each of them having an outer loop, that's kind of eye-watering, and whether we can afford that with a respectable ensemble size is not something I know the answer to. If we can, it would be great. If we have infinite computer size, absolutely I'll agree that we do that, but given we don't, what's the right compromise that we need to make?
So sounds like here your global strategy and the regional strategy are a bit different. Global using EDA, regional using ENKF. Is that scientific region or computational region? Can you elaborate a bit?
It's hard to articulate if I'm honest. So I think with our global system, we are very much influenced by the work of ECMWF, the work of Loïc Baer at Météo France, where they're trying to say if you want to get a good representation of uncertainty, you want to be trying to run as close as you can to a kind of pure Monte Carlo system, where you have your best method for estimating the mean, and then you kind of simulating the uncertainty by adding perturbations to all of the terms that you know that are uncertain. So within that context, an ensemble of data assimilations would satisfy that criteria. Within the UK system, I think we're acknowledging more that we're starting from zero. We know that to get a good convective scale DA, that representing the covariances is very important, and representing the uncertainty is very important. Because you don't have a long data assimilation window where you can kind of use your tangent linear model to spin up the structure of the uncertain features that might be present in the data. So yeah, the thought there is that an ENKF kind of fits that cycle of a kind of a rapidly cycling system that is trying to capture those rapidly evolving uncertainties. So hence it's kind of, we're thinking, therefore perhaps a different tool is the right one to use.
I have a quick question. So you mentioned the trade-off between resolution, ensemble size, and the DA method, and you talked obviously about like the control-pert versus the ensemble of DAs, but as I understand it, you sort of were settling on the 1.5 kilometer for the proposed system. I'm wondering about that versus like ensemble size or something like that. Why settle on 1.5 versus say 1 kilometer or 2 kilometer or something else?
So 1.5 is what we have as a resolution at the moment for the UK system. And because of this effort about retiring the deterministic, it's very much a thought of we want to bring the ensemble prediction system resolution up to the same as the deterministic. And so it's very much coming up towards what we have operationally. I mean, it would be, there was a solid reason for coming up with 1.5. So 1.5, they ran some various simulation studies and found that the diurnal cycle of convection was approximately kind of correctly represented over the UK at 1.5, whereas at lower resolutions it was not. So I definitely think there would be a desire to go higher resolution than 1.5, but I think that's an affordability question that we will do that in future, but probably when we have the next supercomputer.
Like you said, computing isn't infinite, I guess. That's the ultimate problem. So we do have some questions on Slido, or a question from Ricardo Todlane. How do your increments compare between the two DA schemes up high, say around 2 hectopascals? And this is in the case of simulating all the obs.
So if I do that, I think that works. There we go. So I can give you the vertical profile of the increments. And if we do that so this is with the 3D FGAT tests. So if you're kind of looking up at, actually I don't know what 2 hectopascals would be in this, where it would be kind of around maybe level 50 or 60, but I'm not 100% sure, because this level 70 is 80 kilometers. So you can see there are some differences between, say, the Exner function increments. The winds seem to be quite similar. It always seems to be a constant theme that the analysis increments that we get for the winds do seem to be quite similar between the control-pert and the ensemble of independent DAs. What I don't have is I don't have a plot for this at another level or with another variable. I have only got this one. yeah, if I had more plots, I would show them, but I'm afraid that is the only plot I have of a map at the moment.
Okay, let's take one more question on Slido. So do you plan to use AI to increase ensemble size?
Now, that could be a massive question. So the Met Office at the moment, we are planning to look at artificial intelligence, but it's very much in early days. So they have been looking at, for instance, using the Era 5 analyses to try and diagnose or use AI to calculate what a forecast model is, and therefore could we use that AI kind of machine learned model as our forecast model. But yes, the plans for what to do beyond that, I think, are very much kind of in flux at the moment. So I can't really answer the question, but I think the answer will become evident over the next year or two as those plans develop within the Met Office.
Great. And Neill will be here in Boulder one more week, I guess, mostly in FL4.
Yeah, so I'm here until the 19th of September, but the iRogue conference runs from the 12th to the 18th. So I'm definitely around for the next few days and then a kind of day after iRogue as well.
Okay. Let's thank one more time.